In this video, we'll introduce the idea of how to write an amount of accumulation precisely using the scenario of a Mars rover. Here are the main points we'll address in the video. Left and right Riemann sum approximations can be made more precise by increasing the number of intervals over a specified region. The exact total accumulation is the limit of Riemann sums as the number of intervals goes to infinity. A definite integral represents this limit of Riemann sums as number of intervals goes to infinity. As we've seen it before in the previous video, the Opportunity rover landed on Mars in 2004 and has been actively exploring the planet ever since. It is powered by solar cells. As the rover travels across the Martian surface, it kicks up dust which accumulates on its solar cells. Once the solar panels have accumulated 200 milligrams of dust, they will stop providing enough power for the rover to move. The rover is following a 100-kilometer path. The rate at which dust will accumulate on the solar panels can be modeled using this function, where P is the position along the path and R of P is measured in milligrams of dust per kilometer traveled. The goal is to figure out whether the rover's solar panels will accumulate 200 milligrams of dust if it follows this route. To get started, let's look at a graph of dust accumulation function. To approximate the total amount of dust that accumulates, we'll use a left-hand Riemann sum. To start, we have to divide the 100 kilometers into intervals. We'll start by using intervals that are 10 kilometers long each. Since we have 10 intervals and we're using a left-hand sum, the bounds of sum will be 0 and 9. Then we need to find the rate of dust accumulation. We can take these rates from the start of each interval. And then what we do is assume that rate stays constant for each 10-kilometer interval, which will make our graph look like this. And then we know we're using the rate of accumulation at the start of each interval. Then to find the amount of dust that accumulates in each interval, we multiply the rate of accumulation in each interval by the amount of change in position for each interval, which makes our graph look like this. So we know that to find the amount of dust that accumulates in the first interval, we multiply R of 0 by delta P, which in this case is 6 milligrams per kilometer times 10 kilometers. And then we do this for each of the intervals. And then we add these values up to get a total of 229 milligrams of dust that has accumulated. Since we're assuming that the rate of accumulation was constant for each 10-kilometer interval, the number we have computed is an approximation of the actual amount of the accumulated dust. In particular, we can see that the rate of accumulation at the start of each interval is larger than the rate of rest of the interval, which means that the number we have computed is an overestimate of the actual amount of dust that accumulates. In particular, if I highlight these parts of our Riemann sum computation that are contributing to the overestimating interval, we can see that the amount of error in our estimate. This leads us to a question. How can we make our approximation more precise and reduce the amount of error? Let's think about what would happen if we switched from using 10 intervals to 20 intervals. This will mean that we'll switch from k equals to 0 to 9 to k equals 0 to 19. If we use 20 intervals, they would be each 5 kilometers long. Then we need to find the rate of dust accumulation at the start of each interval, and then Again, assume that rate stays constant for each 5-kilometer interval, which will make our graph look like this. And then we know we're using the rate of accumulation at the start of each interval. Then to find the amount of dust that accumulates in each interval, we multiply the rate of accumulation in each interval by the width of the interval, which makes our graph look like this. Like before, we'll add up the amount of dust that has accumulated in each interval. Then this time we'll get 213.8 milligrams of dust. Also, like before, this is an overestimate of total amount of dust that actually accumulates. However, we're only assuming that the rate stays constant over each 5-kilometer interval and not over the 10-kilometer intervals. So this should make our approximation more precise. We can see this by looking at the amount of the error that came from assuming that the rates were constant over each interval. We can see that the error is less than it was before. So the way to make the approximation more precise is to use more intervals. Here we have our Riemann sum with 20 intervals. The orange part of the graph shows the amount of error in our approximation that comes from assuming a constant rate of change for each interval. What will happen to this error if we divide 100 kilometers into 30 intervals? What about 40 intervals? Or 50 intervals? Or 75? Or 100? 200? Or 500? You can see that in this sequence, as the number of intervals gets larger, the amount of error gets smaller, and the value of Riemann sum approaches the actual amount of accumulated dust. We can use the idea of limit to express what is happening here. So R of P is the rate of accumulation in milligrams per kilometer at the position P. And we divide 100 kilometers into n intervals. If we let n get larger and larger and look at the limiting value of this sequence, then we're computing the total amount of dust that accumulates in this solar panel. There is another way to write this limit. We're letting the number of intervals in this Riemann sum go to infinity, and to show this, we turn the summation symbol into elongated S. We write a 0 below and 100 above to show that we're adding up amounts of dust from 0 to 100 kilometers along the path. We're still multiplying the rate of accumulation by the length of the interval, but since we're looking at the limit as the number of intervals approaches infinity, we're no longer looking at a specific value of p. And the length of intervals gets infinitely small, which we show by changing that out to a dp. Like we did with derivatives. This limit, which we call a definite integral, is another way of writing total amount of dust that would accumulate if you added up amounts of dust that accumulate over all the small, infinitely small narrow intervals between 0 and 100 kilometers along the rover's path.